Hi, welcome to this session on responses to forecasts. So forecasts are an important tool for adaptation, although they're not often thought that way. They can ameliorate damages from climate change and from just run-of-the-mill natural disasters. And today we have 3 different papers. We're going to be looking at different aspects of forecasts. So I would like to thank our sponsors for putting this session together. Sponsors include various people who were just on the screen, Edison International, among various other partners. If you would like to contribute to the chat, then you can, we'll have time for Q&A, and I think there's a way that you can go ahead and put something in the chat if you have questions. So you can use this question icon in order to do that, and we'll try to monitor that as best as we can. The order is going to be Mathias Kruttli talking about pricing Poseidon in a second, then we'll have Shrader, and then we'll have Hay. And I will go ahead and introduce a brief organization note. So it's going to be 20-minute talks. We're going to have a little bit of time for Q&A for that speaker afterward. And then at the end, we'll then have some kind of joint Q&A where it actually might be the speakers kind of talking to each other or answering a common question that either I or somebody else poses to them. But we'll kind of see how life evolves between now and then. There could be a lot of evolution between now and then, and we'll see how it goes. So I'd like to go ahead and just get us going with Mathias Kruttli. So Mathias is an economist at the Federal Reserve Board in the Research and Statistics Division. Mathias's research focuses on how climate risks affect financial markets. Mathias received a PhD from the University of Oxford in 2015. And Mathias, please take it away. It looks like you're on stage.
Great. Thank you very much for having us. This paper, Pricing Poseidon, Extreme Weather Uncertainty and Firm Return Dynamics, is co-authored with Brigitte, who just a day ago was still at the Federal Reserve Board in DC, but is now at the San Francisco Fed, and Sumudu Vatugala, who's at Cornell University. So what's the background behind this paper? For this audience, I don't really need to pitch that too much, but there has been an intensification of extreme weather events in the last years. More frequent hurricanes, more severe hurricanes, droughts that lead to wildfires, flooding events, etc. And they're often linked to climate change. What we thought was really missing from this conversation was the uncertainty that's generated for firms by these extreme weather events. And this is somewhat surprising because uncertainty in other contexts has been studied, extensively studied. For example, political uncertainty, right? There are a lot of papers that look at how political uncertainty affects stock returns, how it affects firm investments, etc. And uncertainty in that context is often defined as the expectation of future volatility. And that's also how we will use it in this paper. It's not obvious that extreme weather events will generate a lot of uncertainty for firms. On the one hand, you could imagine that extreme weather events have unpredictable impacts on local labor, demand, or supply chain, and this would increase the uncertainty for firms. But on the other hand, you could also argue, well, vulnerable firms, they could get insurance, they could insure themselves, they could adapt, they could relocate away from risky areas, and that would reduce the uncertainty. If there is really a lot of extreme weather uncertainty, then another question is, well, is it efficiently priced in financial markets? And how climate risks are priced in financial markets has been a topic of that gathered a lot of interest over the last few years because of the potential impact on financial stability. Right? So you could imagine that if you have mispricing of climate risks or climate uncertainty, and then suddenly you have large price corrections, then this could adversely affect financial institutions and could be a risk to financial stability. Now, there are 2 questions that we want to answer in this paper. The first one is, does extreme weather cause uncertainty for firms? And then the second one is, do investors price extreme weather uncertainty efficiently? And what we do specifically is we analyze extreme weather uncertainty at firm level using financial markets data. We have a framework in mind how to think about extreme weather uncertainty. I'm not going to go into too much detail here on the framework because of the limited time, but there are 2 components to extreme weather uncertainty. One is incidence uncertainty, That is about whether, where, and when the extreme weather event will occur. And the second one is about the impact uncertainty. Conditional on the extreme weather event occurring, what will the long-run impact on the firms be that are exposed to this extreme weather event? We use single stock option prices, reactions around US hurricanes. We focus on, or we look at these stock options because from the stock options, you can back out implied volatility. And implied volatility is really a measure of expected future volatility, so how uncertainty is often defined. And we look at US hurricanes just because these are very large and salient extreme weather events. And then in terms of identification, we have a difference in difference framework where we have firms that are located in the forecasted path or the realized path of a hurricane versus firms that are unexposed to the hurricane. And by location, what we mean here, we don't mean headquarter location, but we actually have establishment level data where we see each plant or each establishment of a firm where it's located in the US. So we can precisely estimate how much exposure a given firm has to a given hurricane. Here, an example of Hurricane Sandy, a few days before it made landfall in New Jersey, New York. As the NOAA forecast, at that point, you had incidence uncertainty and potential impact uncertainty because you didn't know where it would hit. And then once it hits, you don't know what the impact on the firms will be. And then at the point when it hit a few days later in the New Jersey, New York area, you had impact uncertainty remaining because you didn't know what the long-term effect will be on the firms with establishments in this region. So what do we find? We find that before landfall, investors remains, the estimates are again very large. The implied volatility is over 20% higher for firms with exposure to the landfall region, and holds across all the industries. And also the impact uncertainty is very slow to resolve. It lasts up to 3 months. What's interesting though is that when we compare this implied volatility increase, so the higher expected future volatility compared to the ultimately realized volatility, then there's a significant underreaction. The realized volatility is much higher than the expected volatility. This pricing inefficiency disappears later in the sample. After Hurricane Sandy, we find that the realized volatility is much more in line with the expected volatility, and also that expected stock returns compensate for this idiosyncratic firm level uncertainty. So we combine different data sources for this paper. On the one hand, we take hurricane wind speed forecasts from NOAA. These are 5 days forecasts available from 2007. Cover 41 storms. Some of these storms make landfall, others not. Then for the after landfall analysis, we use data on the location at the distance from the eye of a hurricane. We have 33 hurricanes to make landfall since 1996. Establishment level data comes from NETS. And then we look at changes in IV, the implied volatility from option metrics, and that data is available from 1996. For our identification strategy, the timeline of the hurricane is quite important. So we have an inception of the hurricane. That's when the hurricane first appears in the Atlantic Ocean or in the Gulf. Then we have a forecast period. The hurricane is forecasted to make landfall. We have a landfall or dissipation period. Then we have a post-landfall period. So for our difference in difference analysis, the first difference is really the pre-period before the hurricane exists, so before inception, to the forecast period or to the landfall period. And then for the second difference in the difference in difference analysis, we look at the firm establishments. Here, just an illustration. Each square represents a county. You have different firms with establishments all over these counties. Then you have a forecast, a hurricane forecast. Certain counties are in the forecast region. And then what we simply do is we count the number of establishments that are in the forecast region and then get an establishment share the forecast exposure for each firm. And that's really just a continuous variable ranging from 0 to 1. Same thing for the landfall region. Here, the orange squares are the counties in the landfall region. We again count the number of establishments in the landfall region. Then for each firm, you have an establishment share of exposed establishments. And this gives us our landfall region exposure, which is again a continuous variable that ranges from 0 to 1. An example of the forecast data we use. So this is Hurricane Sandy 4 days before landfall. Here, this region has a probability of greater than 1% of being hit. So with our establishment level data, we can simply check which firms have establishments in this region and then get the forecast exposure. When we move in a bit to 3 days before landfall, you can see that now a small region also has a probability of greater than 10% of being hit. 2 days before landfall, one region even has a probability of greater than 20%. And 1 day before landfall, we also have this region here that has a probability of greater than 50% of being hit. For the landfall region, once a hurricane makes landfall, so here we have the example of Hurricane Harvey, we look at the eye of the storm and then have different radii around the eye of the storm, like 50 miles, 100, 150, and 200 miles. And then again, we can see which firms have establishments in this landfall region and compute the landfall region exposure. It's important here to realize that we take the eye of the storm and then take the radius around the eye of the storm, because the information on the eye of the storm, where it's located, that's in real time available to investors. And we really want to see how option prices and stock prices react in real time. If you use data from Shrader or FEMA, that's the county level damage data, then this data only really becomes available months after the hurricane has hit, and it wouldn't really be useful for a real-time investor. And now my slides don't move. Can't really see my slides moving. Now it worked. Okay, great. Let's get to the results. So the first regression we run is we want to test for uncertainty before landfall or dissipation. So we have this depend variable, which is the difference, or the log difference in implied volatility before hurricane inception to 1 day, 2 days, 3 days before landfall. We regress this difference on the forecast exposure and have some fixed effects in here. And then if there is a lot of uncertainty before landfall, we would expect the lambda coefficient to be significant and positive. So when we look at 5 days before landfall, we look at the forecast. At that point, you only have a probability of greater than 1% of being hit. You do see that the coefficient estimate, the lambda coefficient you see on the y-axis, is significant and positive. When we move to 4 days before landfall, we get higher probabilities, and we also get higher lambda coefficients. 3 days before landfall, again, lambda coefficient increases 2 days before landfall, and then 1 day before landfall, you can really see how the lambda coefficient is always positive and significant, and how it continuously increases with the probability. So if you increase the probability with which a region is going to get hit, then the uncertainty measured by this lambda coefficient is also higher. So these results establish that there's a lot of uncertainty before landfall or dissipation of a hurricane. What happens after landfall? After landfall, the incidence uncertainty is resolved, and only the impact uncertainty remains. So what we do here is we run a very similar regression to before. Now the difference in the implied volatility is from before inception to tau days after landfall, and we regress it on this landfall region exposure. So the establishment share of a firm in the landfall region that ranges from 0 to 1. And if there is a lot of impact uncertainty post-landfall, again, I would expect the lambda to be positive and significant. This table here shows the results. So we show the results for 50 miles, 100 miles, 150 miles, and 200 miles around the eye of the hurricane. So that's how we define the landfall region. And you can see that the lambda coefficient on the landfall region exposure is always positive and always significant. You can also see how the lambda coefficient drops the further you go away from the eye of the storm. So this was just after landfall. What happens to the resolution of this impact uncertainty? For how long does this impact uncertainty last? So we run the same regression and estimate the lambda coefficient for a range of trading days after landfall here on the x-axis. And what you can see is that first it goes up, so it's a slow reaction. And then around 30 trading days, so 1.5 months, it peaks. And then it slowly resolves and becomes insignificant after 3 months. So this impact uncertainty lasts quite a while, which means investors need time to figure out what's going on with the firm after a hurricane strike. Now we've seen these large increases in implied volatility, so large increases in the future expected volatility. How does this compare to the realized volatility? For this purpose, we compute this variable, the volatility risk premium, which is really implied volatility, so the expected volatility minus the realized volatility. And then we use this as our dependent variable and regress it on the landfall region exposure. And if the lambda coefficient is insignificant, then this would mean, well, the IV is pretty much in line with the realized volatility. If it's negative, however, what it means is that the implied volatility, the expected volatility, is much lower than the realized volatility. So there would be an underreaction. And this is exactly what we find. When we look at prior to landfall, what happens to the VRP? This is the coefficient on forecast exposure. It's always negative and strongly significant in most cases. So this is shows significant underreaction, so investors inefficiently price this extreme weather uncertainty. Same when we look at after landfall, the VRP as the dependent variable, landfall region exposure coefficient is always significant and negative. So again, evidence of an underreaction of the investors. Okay, so overall, over the whole sample period, the investors don't seem to efficiently price the extreme weather uncertainty. So their expectation of future volatility and the realized volatility are not in line. But maybe they learn over time, particularly maybe after a salient large hurricane, they become more aware of this uncertainty and they price it more accurately. So what we do for this purpose is we look at what happens after Hurricane Sandy. Hurricane Sandy was a very destructive hurricane that hit in 2012. And also because it hit New York, New Jersey, it hit the financial center of the US, where a lot of US institutional investors reside. And maybe that increased the saliency of these extreme weather events. And investors started to price them more accurately. So we run the same regression here with the landfall region exposure, where we have the landfall region exposure by itself, but then also interacted with a post-Sandy dummy variable, which takes the value 1 for each hurricane after Hurricane Sandy. And what you can see here is that, as before, the coefficient in the landfall region exposure is negative and significant, but the coefficient on the interaction is positive and quite large. So meaning that this underreaction really goes away later in the sample. Another thing we can look at then is the expected returns. So we've shown, okay, there's a lot of extreme weather uncertainty, but do investors really require a compensation for this extreme weather uncertainty? The theory on this is mixed. On the one hand, you would say, well, these extreme weather events are a local phenomenon, right? They hit a few firms, but they don't hit the US in general or the US market in general. So you could argue, well, you can simply diversify this risk. And in that case, you wouldn't expect to see higher expected stock returns for these firms that are affected by the hurricane. But there are theories around her, for example, Levy in 1978 and Merton in 1987, that make the argument that even such idiosyncratic uncertainty should lead to higher expected returns because investors and markets are segmented. The empirical evidence is a bit mixed on that. Eng et al. Find that this is not the case. Idiosyncratic uncertainty doesn't give you higher expected returns. Fu finds it does. What we can bring to the table here, we have this unique empirical setting where we have purely exogenous shocks, so these hurricanes, and we can get at this question through that channel. So we run a similar regression to before, but now the dependent variable is the difference in excess returns post-landfall and pre-inception. So again, this excess return here, the pre-inception excess return, is before the hurricane actually exists, and then the post-landfall excess return is after landfall. And we regress on the landfall region exposure variable. What do we find? When we just look at the landfall region exposure variable, there's a negative effect in excess returns. So there's really no compensation for this extreme weather uncertainty, this idiosyncratic uncertainty. But we do the same thing as before. We incorporate this post-Sandy variable and interact it. And then what we find is that there is actually a compensation. There are higher expected returns for firms with establishments in the landfall region. And this is important to know. And if we want to learn about climate change and how climate change is priced, we want to know whether investors actually get compensated for taking on these climate risks that's often idiosyncratic. So to conclude, what we do in this paper is we show that extreme weather events cause substantial uncertainty. The results hold across different industries. I didn't have time to show this in the presentation, but it's in the paper. And we find that before landfall, there is substantial incidence uncertainty and expected impact uncertainty. Once the hurricane hits, there's only impact uncertainty that remains. And this is also very large, with implied volatilities increasing over 20% and remaining elevated for up to 3 months. However, there are very significant pricing inefficiencies. Markets underreact to repeated events like hurricane. And it took a very salient and large hurricane to get rid of this pricing inefficiency, which is somewhat worrisome when you think about other climate risks that are novel and that investors have little experience with. Thank you very much, and I'm looking forward to the questions.
Great, thank you, Mathias. So we're happy to take questions. I think we might have to do that via the chat box. So you can find the question mark on the lower right, and if you type a question in there, I'll read it out. So the bottom right of your screen, there's some questions and answers thing, and if you click in there, I think I can read what you type. While people possibly work on that, I'll take the chair's prerogative and ask a question. So I was intrigued by the variance risk premium finding, because it's obviously opposite what you probably would have expected going in doing the calculation. And I was wondering how much of that is because you're just using implied volatility, probably from some somewhat near the money option as your measure of ex ante expected variance. If it is like a really left skewed distribution, it's not a model free method doing it that way. Like it only really works if the distribution is actually log normal. And so you might get a very large underestimate of expected volatility by only looking at IV near the money rather than a model-free measure that would allow for variance details to be captured.
That's a very good point. We only use the IV currently. That's a model-based method. We do have quite a delta range from like 0.2 to 0.5. So it's not just very at the money options. We do have a larger range in there. But we certainly have to look at the model-free implied expected volatility estimates as well. That's actually something that a referee pointed out. So your comment here is spot on, and we will have to do that.
Okay. Let me know if I should be looking somewhere else. We have another few minutes. I'll also ask a question about Hurricane Sandy then. Yeah. So I was intrigued about the pre and post Sandy results, obviously. Is there anything you can do to let us know that this is really due to Sandy? Like, could you look at how, could you actually show a plot of how it changes over time in a more continuous fashion, or do some geographic diff and diff that can convince us that it actually is about Sandy hitting and not about some other change in the market that occurred over this period?
We did look at other hurricanes. We looked, I mean, in our sample, it's really, you have Hurricane Sandy, which is a large one, and then Hurricane Katrina, which was even larger, but occurred much earlier in 2007. Or 5. Yes. And for Hurricane Katrina, we didn't really find this effect, this jump in the pricing efficiency, how it changed. Yeah, it would be nice to have an even more clear-cut way to show that this is due to Hurricane Sandy and not another change that happened in the market. Maybe we could try to do something with institutional investors that resided in the New York and New Jersey area, and some institutional investors that didn't reside in that area, and see whether we can get some cross-sectional difference.
Yeah, that would be helpful. That would be great. So you only have 2 hurricanes in the sample?
Oh no, sorry.
What
Not 2
years
hurricanes. It's our sample is from 1996 to 2017, and we have all the hurricanes that occurred during this sample. I was talking about like the major hurricanes that we have in the sample. And this is Katrina and Sandy.
Got it.
And then for Katrina, we thought, well, maybe. And I thought maybe for Katrina there was a similar effect, and we tested that, but it wasn't the case.
Yeah. Cool. Then I think what we'll do is we'll go ahead and move on to Jeff, and we can reserve time at the end, the extra handful of minutes, for a group conversation, which could be nice. So thank you, Mathias, very much for your presentation. And Natalie, if we It looks like I got lost, but Jeff, can you hear me? Okay, you can hear me if you can't see me. Great. Okay, so now I'm pleased to present Jeff Shrader. Jeff is an environmental and labor economist at Columbia University School of International and Public Affairs. He uses theory and data to study how beliefs affect decision-making, the role of information, especially professional forecasts, and shaping beliefs, and the effect of forward-looking behavior and empirical analysis. His work focuses on estimating damage from climate change, accounting for how individuals and groups use information like weather and climate forecasts to anticipate and adapt to a changing climate. So the last paper was on forecasts of natural disasters. This paper is on forecasts of more run-of-the-mill weather. And full disclosure, I'm a co-author in the paper, so I will try not to give Jeff any extra time because of that. So Jeff, take it away. You have 20 minutes. And I can't hear you, at least. Jeff, I can't hear you. I don't think anybody else can. So I wait for Jeff to come back. This is our forecast for April 30th, 2021. As you can see, there are lots of pretty colors. Parts of the country are hot, parts are less hot.
All right. Can you hear me now?
Much better. Yep.
All right. Great. Well, sorry about that. So yeah, this is, I'll just say this, joint work with Laura Bockinson and Derek, and it's on routine weather forecasts, as Derek mentioned. And these are the types of forecasts that you see if you go and check, for instance, weather.com, or if you look at your smartphone, or if you navigate to the National Weather Service website. This is a forecast that I pulled off of the National Weather Service website in April, or if you watch your local nightly or morning news. So these are the types of routine weather forecasts that a lot of us interact with on a daily basis. Survey evidence actually says that the vast majority of people view these forecasts daily. So they're widely used, widely viewed. There's also a lot of effort that goes into their creation. So there's this kind of remarkable global effort to gather data from around the world every hour of the day, every day of the year, assimilate that data, share it with different weather forecasting agencies, and then run it through very sophisticated physics and statistical models to produce the forecasts, and then ultimately disseminate them, usually for free, to the public. So really widely used forecasts, widely viewed forecasts, a lot going into their creation. Given all of that, it was surprising to me, and it might be surprising to you, to find out that we know as scientists, almost nothing about the value or the benefit that these types of routine weather forecasts bring. It's easier to get a sense of how much effort goes into the creation of the forecasts. So putting some dollar values on this, in the United States alone, the US federal government spends something like $4 billion on the creation, maintenance, dissemination, and upgrading of forecasts. This is largely spent by the National Oceanic and Atmospheric Administration, and the National Weather Service is part of that administrative branch. And this is things like launching weather satellites. This is things like routine maintenance and creation of forecasts, as well as new R&D. Estimates are that the private sector probably spends at least another $1 billion on forecasts in the United States. And this is organizations like IBM, who owns the Weather Channel. So something around $5 billion per year is spent on the creation, dissemination, and upgrading of forecasts. Much less is known about the benefits that these forecasts bring. If you ask NOAA what the benefits of forecasts are, they often point to this 2009 study by Jeff Lazo and co-authors that used a stated preference survey, essentially going out and asking people, how much do you value forecasts, to arrive at an estimate that the median household in 2006 was willing to pay $260 per year for the existence of the weather forecasting system. Stated preference surveys are widely used, but of course they're not without controversy, especially for something like weather forecasts, which are quite ubiquitous, and it might be hard for people to reflect on the value they have from, say, the existence of a weather forecasting system. There are, in contrast, no revealed preference estimates for the value of routine weather forecasts. And that's where our paper comes in. We're going to provide the first estimates of the benefits, or at least one benefit that routine weather forecasts provide, using real behavior that people are engaged in, so a revealed preference estimate. The benefit we're going to focus on is related to extreme temperature and mortality. So in this project, we're trying to understand the benefit that forecasts might bring in terms of allowing people to avoid mortality from extreme temperature, extreme heat, or extreme cold. The focus on the temperature and mortality link is for a couple of reasons. One is just practical. We have quite rich data on mortality events in the United States that we can link to weather and weather forecasts. So it allows us to provide these revealed preference estimates. But there are some more fundamental reasons to study the link between mortality, temperature, and forecasts. First, temperature is the single deadliest form of extreme weather. So if you look at all sorts of extreme weather, tornadoes, hurricanes, big storms, temperature is actually the one that's responsible for the most deaths in a given year. And this is expected to get even worse under climate change. So lots of work in economics and epidemiology, including a very recent paper by Tammy Carlton and co-authors in 2020 suggested that direct heat-related mortality is going to be one of, or the most important damage from climate change. The National Weather Service also cares a lot about reducing mortality when they are designing and implementing new forecast products or changes to forecasts. So we think, even though this is just one of the many potential benefits from forecasts, this is an important one to focus on. And so in this project, we're gonna go out and try to look, how effective are routine weather forecasts for helping people avoid mortality from extreme heat or extreme cold? We're going to do that by putting together three main data sets. The first is on mortality. So we observe mortality, all mortality events in the United States from 2005 to 2017. We know the day that the death occurred, and we know the county in which the death occurred. So from this, we can construct county level daily measures of the mortality rate. We put that together with temperature data and temperature forecasts. The temperature forecasts are the ones issued by the National Weather Service. They're the ones that you would go and find on the National Weather Service website if you were to check it right now. We aggregate those up to the county daily level. So the forecasts are issued on a spatial, fine resolution spatial grid. We population weight that and generate average temperature within a county on a given day. For realizations of temperature, we use PRISM data. This is a widely used data product that's derived from weather station observations. And we again aggregate that up to the county day level, following the same procedure that we do for forecasts. We have some control variables as well that I'll talk about more when I introduce the regression. These are things like population, shares of population, different age groups, other realizations of weather like rainfall. In robustness checks, we add things like local air pollution measures to try to account for correlation between temperature and air pollution. And I'll describe these in more detail when I talk about the regression. But putting all these three initial pieces of data together, we can get some initial evidence on the relationship between forecasts and mortality just by looking at the raw data relationship. And I'm showing you that here with two figures. In both of these figures, I'm plotting just the raw data relationship and then a local linear regression through that raw data, relating the daily mortality rate on the y-axis to forecast error on the x-axis. So forecast errors are negative or positive. Positive forecast errors mean that the forecast was too hot relative to the truth. Negative forecast errors mean the forecast was too cold relative to the truth. And a zero forecast error means the forecast was right on. And I'm going to show you the relationship between forecast error and mortality for two different temperature realizations. The left figure shows you times when the realized temperature was cold, so less than 5 degrees C, less than about 41 degrees Fahrenheit. And the right figure shows you the relationship when temperatures turned out to be hot, so greater than 30 degrees C. So this is like high 80s Fahrenheit or into the 90s. These types of high temperatures are these types of hot temperatures are extremely hot for the US. This is average daily temperature. So about 1% of days in the United States have temperatures above 30 degrees C. These types of cold temperatures are kind of moderately cold for the United States. They're about 20 to 30 times more common than the hot temperatures. Focusing first on the cold temperature figure on the left, we can see that there's a clear relationship between mortality and forecast error in the raw data. Negative or positive forecast errors are both associated with elevated mortality. So if the forecast misses in either direction, that's associated with an increase in mortality. If the forecast is accurate, if we're around zero forecast errors, or right in the middle, then that's associated with the lowest level of mortality. If this has a causal interpretation, it suggests that there is substantial value to reducing forecast error to issuing more accurate forecasts, and therefore it suggests that forecasts are very valuable for avoiding or helping people avoid mortality. There's also a strong relationship between forecast error and mortality at hot temperatures, so in the figure on the right, but the relationship is kind of interestingly different. There's substantially elevated mortality on days when there are negative forecast errors. So if I tell you it's going to be or if I tell you it's going to be moderately hot, but it turns out to be extremely hot, so the forecast was too cold, then that's associated with substantially elevated mortality. In contrast, if the forecast misses by being too pessimistic, by telling you it's going to be extremely hot, but it just turns out to be very hot, then there isn't really substantially elevated, or that's not associated with substantially elevated mortality. So an interesting asymmetry on hot weather days, and this clear U-shaped pattern on cold weather days. That's the pattern in the raw data. We want to account for some potential confounders, seasonal patterns, things like that. So we're going to move now to a regression framework and see if this same pattern holds. The regression is going to use the following estimating equation. This estimating equation is going to relate our outcome variable, which is mortality per 100,000 people in county C on day T as our left-hand side variable, to flexible functions for temperature, capital T here, and forecast error, which is the lowercase e term. So we have flexible functions both for realized temperature and for forecast error. The flexible function we're going to use for realized temperature, this term that involves the capital T's, this follows prior work from Deschênes and Greenstone and Barreca, Clay, Deschênes, Greenstone, Shapiro in their 2016 JPE paper. So we're going to specify a series of bins. If temperatures fall in those bins, we're going to allow each of those temperature bins to have different effects on mortality. We then interact those temperature bins with linear splines, one knot linear splines over forecast errors in the baseline results, where the knot is placed at the median forecast error within each bin. So this allows for different effects of positive and negative forecast errors to try to capture, for instance, some of those U-shaped relationships, if they exist, that we saw in the raw data. Those flexible functions, we then estimate using a distributed lag specification. So we estimate them over multiple days, so we can calculate cumulative effects. Prior work in epidemiology and economics has shown that there can be important delayed effects of temperature on mortality. For instance, cold weather sometimes takes a few days for the mortality to manifest. Hot weather, there's this so-called harvesting effect, where there might be a lot of mortality immediately, but then there's lower mortality in subsequent days. So the results I'm going to show you here today are 1 week cumulative effects. We've run our estimates out to 8 weeks in additional results, and the forecast error results look very similar to what I'm going to show you here today. The rest of the specification are controls. In our baseline specification, we again stick very close to Barreca et al.'s 2016 JPE paper. So we have location fixed effects, location by season, by month fixed effects to account for fixed features of the location, as well as different seasonal patterns in different locations. We interact month fixed effects with location population shares in different age categories, because we know people in different ages are affected differently by temperature. We have time fixed effects, so day fixed effects. We also control for realized rainfall in the baseline specification. And as I mentioned in robustness checks, we've done other weather controls as well, like wind and atmospheric pollution. The standard errors are clustered at the weather forecasting office level. Weather forecasting offices are collections of counties, and each weather forecasting office is a NOAA organization that's in charge of issuing forecasts for that collection of counties. So a given weather forecasting office will issue the forecasts for those counties, and therefore it's a natural level at which to cluster our analysis. Estimating this equation, we can work to understand the effect of realized temperature on mortality and then forecast errors on mortality. I'm going to show you the effect of realized temperature first. That's given in this figure here. So we have mortality rate on the y-axis, and we have daily temperature realizations on the x-axis. This is a result that's been found in lots of prior work before, so I'm not going to dwell on it for very long, except to say that like prior work, we see that extreme cold and extreme heat both lead to elevated mortality. This is the short run cumulative effect. So this is over 1 week. If we look over longer periods of time in our sample period, this relationship does look slightly different. In particular, the hot weather effect goes down as we look over longer cumulative effect periods. But we're really focused not on this realized temperature effect, but the role of forecasts and forecast errors. So that is shown in the following two figures. These figures are the regression analog of the raw data figures I showed before. So on the left, we have the effect of forecast errors when the weather turns out to be cold. On the right, we have the effect when weather turns out to be hot. As we saw in the raw data, forecast errors in either direction lead to elevated mortality when the weather turns out to be cold. So relative to a day with very low forecast error, so forecast error near zero. We have elevated mortality if the forecast misses by being too high or too low, and the weather turns out to be cold. In the right figure, we see, again, the suggestion of something like an asymmetric effect. Negative forecast errors are really bad. So if the forecast misses too low, then mortality is substantially elevated. So again, if I tell you that it's going to be, if I, the forecaster, tell you it's going to be, kind of hot, and it turns out to be very hot, then mortality is substantially elevated. If the forecast misses in the other direction, however, if I tell you it's going to be extremely hot and it's just kind of merely hot, then mortality is not as elevated. So note the difference in scale between the left and right figures here. Both these figures, though, show that there is this convex relationship between forecast error and mortality. And so there's going to be potential benefit from reducing forecast error, from issuing people more accurate forecasts. To calculate that benefit, let's focus in on the hot temperature figure and work through an example of one forecast error reduction. So imagine that we're on the far left of this figure. We have a forecast that has a negative 2.5 degree forecast error. That would be a substantial error according to NOAA. If we were to reduce that error by 1 degree C, so reduce the negative 2.5 degree error down to a negative 1.5 degree error, we would reduce the daily mortality rate by about 0.05 deaths per 100,000 population. There are something like 328 million people in the United States. So that translates into 164 lives saved from reducing forecast error by 1 degree C. So that's a lot of lives saved by making the forecast more accurate. Of course, these negative forecast errors are really bad in terms of elevated mortality. So if we look at both negative forecast errors and positive forecast errors in this figure, the expected reduction in mortality from a 1 degree C improvement in the forecasts, so a 1 degree C reduction in forecast error, is about 123 lives saved across the United States on a day. So giving more accurate forecasts on hot days can allow people to avoid mortality to a substantial degree, about 123 lives saved in expectation for a 1 degree C more accurate forecast. The effect on cold days is less. The mortality relationship between mortality and forecast errors was less steep on cold days. In expectation, we would say that there's there'd expected to be about 41 lives saved from a 1 degree C forecast error reduction on a cold day. But looking across the year, cold days are currently much more frequent than extremely hot days. 20 to 30 times more frequent than those extremely hot days right now. Monetizing all of that with the EPA VSL of $9.76 million, a reduction in forecast error by 1 degree C would be worth about $22 billion per year. So if you're able to permanently reduce forecast error by 1 degree C, that would be worth $22 billion per year. So really a substantial benefit in terms of avoided mortality. Is that 1 degree C reduction reasonable? The figure on the right suggests that it could be. The figure is showing typical forecast errors for NOAA forecasts, the 1 day ahead NOAA forecast, on the far left, the 6 day ahead NOAA forecast, and then some statistical forecasts. In this paper, we're currently focusing on the 1 day ahead forecast. It has a typical forecast error of 1.4 degrees C. If you look at something like a statistical forecast, an AR1 forecast, it has a typical error around 3 degrees C. So compared to a statistical forecast using similar information, the NOAA forecasts are reducing forecast error by much more than 1 degree C already. So forecasts, in conclusion, are generating substantial value in terms of avoided mortality. It seems like people are able to use the information in forecasts to avoid mortality from extreme weather. Currently, a lot of the value comes from cold days, avoiding mortality on cold days. But we saw that on a per day basis, forecast errors on hot days are more deadly. So as the climate changes, one way to promote adaptation and help people adapt to a changing climate, adapt to more frequent extremely hot days, is going to be to give them more accurate forecasts on those hot days so they can avoid mortality from that heat. Thanks.
Great, thank you, Jeff. And we have a handful of questions for you. So first, somebody asked a question about early on. This is Andrew Martinez is asking a question about what forecast horizon you're using in those results.
So I think I answered this after the question came in, but thanks for the question. It's the 1 day ahead forecast in the results I showed you here, but NOAA issues forecasts out to 7 days. Places like weather.com issue them out to 10 days, but out to 7 days is what NOAA does.
And there's another question from Louis Chua about why the asymmetry doesn't arise at cold temperatures. The asymmetry and forecast effects.
That's a really interesting question. It's not totally clear to me. I think that's a fascinating result to dig in more. One thing that we do see is that the causes of death on hot and cold days are quite different. So the causes of death on hot days are acute exposure related deaths. So it's people who are exposed to the heat. They die from cardiovascular or related causes. Whereas cold weather deaths are broader, and a lot of them are things like infectious disease. And so it seems like people are able to match their behavior to the state of the world better when the weather is cold. Whereas with the heat, it's really like if I'm led to go outside and expose myself to the extreme heat by a forecast that's too optimistic, then I experience some acute mortality. And so that's one of the results that we're really curious to unpack more. And if you have thoughts or suggestions on what we should do to explore that, then I'm all ears, because I think that's an interesting and fascinating result that we found so far.
And Victoria G asks, are we worried about lag temperature being correlated with forecast errors?
In principle, yes, but I mean, we're estimating distributed lag models. So in a simple statistical sense, we're accounting for that. So the short answer is it's accounted for in the statistical analysis. The other response is that these forecasts are really good, right? So there's this idea of forecast sufficiency. If the forecast is sufficient for the information that goes into the forecast, then the other information won't be correlated with your conditional on the forecast. The information won't be correlated with some future weather. And we do find that to be the case here, right? Like NOAA is pretty savvy about issuing these forecasts. And so these forecasts are sufficient for prior information. And so there's no correlation, for instance, between past weather and future weather conditional on the forecast.
Cool. And really quickly, before we get to another substantive question, there's a clarification question from Astrid called us about the difference between 164 and 123 lives saved. She was wondering if they're both 1 degree, or he or she was wondering if there's 1 degree lower error, but different sides of the curve. I think that was right.
Yeah. So the 164 was just if we were to reduce forecast error on the left side of that figure, right? On the highest marginal value side of the figure. The 123 was the expected value across the entire figure, right? So if you weren't able to just reduce forecast error on the if the forecast error reduction wasn't all coming from the side of the figure where the marginal value is highest, it's the expected value of reducing forecast error by 1 degree on a hot day. That's 123. Yeah, thanks for the clarification.
And there's a question from Luis Benias. Does climate change complicate the ability to forecast accurately, or is forecast accuracy more dependent on things like R&D, instrumentation, et cetera?
That's an open question in the meteorology world, as far as I understand. I'm an economist, so a meteorologist could answer this better than me. But my understanding from the literature, last year, for instance, there were 2 competing papers published in top meteorology journals. One said forecasting is going to get harder under climate change. The other said actually forecasting is going to get easier under climate change. In some cases, higher weather volatility makes it easier for meteorologists to forecast. And so even though we expect climate change will increase volatility of a lot of weather systems, that might actually make forecasting more accurate. So it's an open question. It's certainly one that the meteorologists are interested to resolve. And once they resolve it, I'm happy to write the paper on the climate change implications of that resolution. Yeah. The reduction, improvement. Oh, sorry, Derek. The improvement in forecast that has gone on over the last few decades has really been much, rich data, better assimilation, The techniques haven't changed too much, right? The physics have been understood for a long time. So it's been a lot about data, computer processing power, assimilation of data, things like that.
So one quick note for the people asking questions, it's easier if you put them all in the one with the question mark. That way I don't have to swap back and forth to read them all. So there's 2 questions left. So Remy had a question that was kind of the same question I was going to ask about whether it's actually harder to improve the forecast more now that we've already got good forecasts. Like how would you actually do that and how costly is it? And then Pierre Mirel has a question about did we try nonlinear relationships as well? So if you had a U-shaped relationship as opposed to a V-shaped relationship, the counterfactual benefits from reducing errors could look different if there's more massive errors towards 0. You have about 1.5 minutes left, so feel free to take those however you'd like.
On the V versus U, we've estimated a variety of different things, and the results are pretty similar, whether we estimate the V's that we're estimating here, which are just a nice parsimonious specification, or something that's a little bit more flexible, because a lot of the value is coming from big forecast misses. For Remy's question, this is also an open question. People have been kind of doomsaying for a long time that our ability to improve forecast has run out. And yet, if you look, forecasts have just been improving linearly or more or less linearly for decades. So there is kind of a well-established, there's this idea of chaos that gives us a limit on how much forecast can be improved. But so far, we haven't hit the limit on forecast improvement. They just keep getting better on average year after year after year. At some point, that's got to run out, but so far we're continuing to be able to improve them.
You could have swapped out forecast for Moore's law and chaos for quantum effects, and it'd be a similar conversation. Yeah. Okay, great. Thank you, Jeff. So I think it's time to switch to I. We can go ahead and swap the slides. All right, so we've talked about stock markets. We've talked about death. And so what is left to talk about except for loans? So I'm happy to introduce Ai He. Ai is an assistant professor of finance at the Darla Moore School of Business. She completed her PhD in finance at Emory University. She has previously studied at Shanghai Jiaotong University. Her primary research interests include empirical asset pricing, banking, and financial institutions. So Ai, you have 20 minutes. Please take it away.
Okay. Oops. Yeah. Thank you, Derek. Can everybody hear me?
I can hear you.
Yeah. So thanks for involving this paper into the program. So the title of our research is the rising tide lifts some interest rates, climate change, natural disasters, and loan pricing. So this is a joint work with my let me show their names. Yeah, this is a joint work with my co-authors, Ricardo Correa from Federal Reserve Board, Christoph Heffer from Emory University, and Hugo Leo from University of Georgia. So basically in this paper, we study how the corporate funding cost, specifically the loan cost, get affected by the increasing occurrence of natural disasters, which are caused by climate change. So first of all, I want to talk more about the big picture of this project. So I don't think I need to emphasize more why we're studying climate change in today's perspective, right? So it's not just a climate-related thing. It actually can affect the global economies. So based on this, actually in the finance market, from the policymakers' perspective, like Federal Reserve, for the first time, they highlight climate change as a potential threat to the stability of the financial system, which happened in last November. And most recently, in July this year, the ECB Governing Council also expressed the same concern that the climate change should be considered into their monetary policy framework. So this is a broader policy and economic background of this project. So how can we fit our research in the literature? So basically, when we talk about climate change, most people are thinking about something that not happen immediately. The effect will not happen immediately, but will be a long-lasting effect which will occur in like 50 years or 100 years, right? So for example, when we talk about the sea level rise, we know that it will not affect our life immediately, like next year, but it will definitely be something that will happen after 50 years or 1 century. So because of that, how can we link climate change to financial market from today's perspective? The existing literature focuses mostly on the long run effect. So people are looking at those infinitely lived assets like equity or real estate and evaluate how their long-run discount rate is affected by our estimation about climate change risk in the future. But how about the debt market? When we talk about debt market, it's a little bit hard to say here. The reason is there is a mismatch between the maturity of financial instruments like debt with the long horizon of climate change. So for financial instruments like debt, the average maturity is much smaller. It's like 10 years for municipal bond, or even less than 10 years for corporate bond. Therefore, if we directly link the financial instruments like that with climate change risk, which will happen after 50 years, it's very hard to find an immediate effect. That's why in recent study in municipal bond, people find that only by very recently that investors start to project long-term sea level rises as a risk into the municipal bond pricing. So for us, when we're studying the corporate bond, we try to occur this mismatch issue. So a unique link or unique channel we find is the severe weather event. So we take extreme weather events as a potential channel through which climate change can impact banks and firms from today's perspective. So we find that there is an immediate and physical effect of climate change on corporate funding cost through the occurrence of big natural disasters. So this channel, our selection of this channel is supported by recent studies. Like I think in yesterday and today's different sessions, some study might also mention that to see that the severity and the frequency of specific disasters can be directly linked to climate change. So like hurricanes, floods, and wildfires, those are all climate change directly linked disasters. So we pick up those disasters and study how those disasters impact the performance and the credit worthiness of borrowers, therefore make banks update their priors about future severity by observing those natural disasters, therefore to increase the loan spreads to those firms who are suffering those disaster risk. So that's a basic idea of this paper. So our selection of using natural disaster as a channel also gets supported by anecdotal evidence. So for example, when we look at major banks in the United States, when we screen their 10K filing recently, like 2 years ago, we find all the banks express their concerns of a worsening trend of climate disasters. And many of them even name specific natural disasters which they think can be linked to climate change. So like floodings and hurricanes or wildfires, those are most frequently mentioned. So as quoted in PNC's 10K filing, banks think that climate change may increasing the frequency and the severity of adverse weather conditions. Therefore, it will affect the creditworthiness of their customers, therefore affect the value of assets securing loans. So that's the basic idea why we take a look at the natural disasters impact on banks' loan pricing decision. So let me show the basic empirical framework in this paper that we're studying. So for example, like there are different locations across the country, and the firms are located in those different locations. So if we look at New Orleans, suppose there is a firm A located in New Orleans, and we know that New Orleans is a disaster, is a hurricane. Let me take a hurricane as an example. It's a hurricane-prone region, right? So the most direct approach for us to study how natural disasters affect loan pricing is that take a look after hurricane hit New Orleans. So for example, Katrina, after Hurricane Katrina attack New Orleans, firm A is directly hit by this disaster. Therefore, we can look at how banks change their loan pricing to firm A. So that's a very straightforward approach. Meanwhile, we need to pay attention that if we take this setting, there is actually confounding effects, right? So effect one is that firm A in New Orleans get affected by hurricane. It suffers physical damages, and it also has increasing number of credit needs for future future recovering from the disaster. Therefore, banks need to reconsidering about the loan pricing to firm A. So that's the direct effect. The second effect is the occurrence of Katrina update banks prior about hurricane disaster risk. Therefore, this change of banks' expectation makes banks to change their loan pricing decision to firm A. So those two effects are very hard to distinguish in this straightforward approach, while we want to tease out the second one because we want to really measure how banks change their expectation. So in our study, actually, we take another approach, which is more complicated, but also more intuitive. So, okay, so rather look at firm A, we look at the firm B in another location, like Houston. So for Houston, firstly, based on historical disaster records, it's also a hurricane-prone region. Meanwhile, if we just look at the Hurricane Katrina per se, Houston is not affected. Therefore, for firm B in Houston, it's not affected by this hurricane, but it is affected. It is at the hurricane risk. So we can clearly tease out the two compounding effects I mentioned before and look at how after banks observing hurricane happening somewhere else, how banks increasing or change their loan pricing to firms in another location which suffer the same risk. And of course, as a control group, we look at other firms in other locations, like firm C in Dallas, which is totally not suffering any hurricane risk based on historical records. So that ideally we're comparing two types of firms, firm B and firm C. And if everything else controls equal, the only difference of those two firms is that one is located in at-risk regions, the other is not. And we test how the loans issued by the same bank to those two firms at the same time get affected after hurricane happened somewhere else. So that's the basic empirical setting that we're testing. Of course, I kind of simplified the setting, the true setting in our papers. Firstly, we're not just look at a hurricane. We look at also other type of climate-related disasters like floods and wildfires. And secondly, we consider about firms' footprints across the country to consider to which level it is at the risk regions. So rather than look at one location, because we know like typically for firms, especially public firms, they have factories all across the country. So we do carefully consider that. So what is the, okay, so, yeah, I think I already explained this. So before I go to the empirical testing results, let me briefly talk about the data. So firstly, we have this detailed graphic footprint of each firm across the country. So we have the firm level, therefore we can have the firm level information of the, we can have the location level information of the firm. Also, we get disaster data from shelters. So this data tells us each disaster's type, location to the county level, and also the time. For the dependent variable, we use the DL scan for loan origination, and we also have the loan secondary market trading data. And we use CompuStat to control all the standard firm level and the bank level variables. So the final sample we study is from 96 to 2019, so more than 20 years loan origination data. And about the disasters, so we take a look at 5 types of disasters: hurricane, earthquake, wildfire, flooding, and winter weather. So the one marked as red here, based on the climate science literature, they are climate change related. While the blue ones here, like earthquake and winter weather, they are not climate change directly linked. So we use those blue ones as a placebo test to show whether it's because of climate change or it's just because of natural disasters. So we find that the loan pricing change only happened for those red types. For the blue types, we don't find we don't find the loan pricing change. So that indicates, it means banks are reacting not just to natural disasters, they're actually reacting to climate change. So I will skip this. So let me quickly talk about the basic model we're testing here. So basically, we look at the loan spread. So that is the loan issued by Bank J to firm I in month T. And there are several variables we pay attention to. First one is the recent disaster variable. Let me use hurricane as an example here. So like recent hurricane indicates whether the month T is within 3 months after a hurricane happened in this country. So this is a time dummy. And the blue variable, which is indirect hurricane, is a firm time level variable. So it indicates whether this firm, based on its location and the historical disaster records, is in hurricane-prone regions. So for example, like firm B, like firm in Houston, will have indirect hurricane dummy as 1, while firm in Dallas will have indirect hurricane dummy as 0. Okay, so basically we pay attention to the interaction of those 2 terms. So if our story goes well, like after a recent hurricane happens, for those with indirect hurricane risk, banks will change their loan pricing, then we should expect to see the beta 1 is significant. And we are, in our hypothesis, we think banks will increasing their loan pricing to those firms because they're concerned about hurricane risk. So based on that story, we should be able to see a significant and a positive beta 1. Of course, we do a very careful work here. So we have all the control variables on the firm level and on the bank level, XIJT. And more importantly, we have the bank year fixed effect here. So that helps us to control all the bank firm variations, so that ideally we're comparing the loans issued by the same bank at the same time to 2 different firms. So the only difference comes from whether this firm is at hurricane risk or not. So let's see what we find. So here's our main result. So we find that if we test based on hurricane you can see that the beta 1's value varies from like 17 basis point to almost 20 basis point, which means that after the hurricane happens somewhere, on average, banks increase their loan pricing to hurricane risk firms by almost 20 basis points. And as a placebo test, as a comparison, if we test it by earthquakes, oops, let me show here. Okay, I think I cannot use the hyperlink based on my remote control for the slides. Anyways, so if we look at the earthquake, we don't find similar results. And also, if we look at the winter weather, we don't find similar results because those are the blue disasters as I marked before, which are not linked to climate change. Meanwhile, if we look at the wildfire and the flood, we find the very similar pricing effect for those two climate change related disasters. So we interpret it as an evidence to show that banks change their prior to climate change risk, and therefore they change their pricing, the loan pricing. And we studied deeper about the economic channel behind that. So we find that this pricing effect is related to banks increasing attention to climate change. So, for example, when we use Wall Street Journal index to mark how high the attention could be, and this Wall Street Journal index basically measures the climate change vocabulary appears on Wall Street Journal, and we find that this pricing effect peaks when this index is high. So that means when the general public pays more attention to climate change risk, this pricing effect is even higher. And also similarly, we look at the loan pricing in the secondary market, and we find a similar pricing effect. So basically, when after a hurricane happens, for those at the hurricane risk, their loan pricing in the secondary market, their price of loans in the secondary loan market gets decreased. And we also take a look at the bank's internal channel to see how banks' internal risk assessment get changed in the same setting, and we find that banks actually in the internal setting, actually banks have higher risk measurement of the natural disaster risk. And here are a few cross-section robustness cross-section tests we conduct. So we carefully consider whether
you should go ahead and wrap up soon. That way people have time for questions.
Yeah, so I actually already covered the key part. I would just briefly talk about the robustness test. So basically, we find that banks with higher market leverage or more tangible or has no investment grade, they are suffering higher interest. They're suffering higher pricing effect, and also if the disaster's magnitude is higher, this effect is even larger. Okay, and I will skip the rest of part of discussion, which we talk about more robustness test. And overall, to wrap up the finding, basically our finding shows that climate change already shapes economic risks today. It's not something we should wait to see happen after 50 years. And we provide a study to directly link climate change to present-day corporate loan cost. So I will stop here, and I will looking forward to answer the questions.
Great, thank you. Please put questions in the chat, ideally using, I guess, the question mark chat room. A lot of really understand the difference between the two of them. And can you see the question mark chat room?
Yeah, I think I can see.
It looks like there's a way to actually reply directly to people in case we were to not have time to hit them all, like from past talks. Okay, so if anybody has a question for please go ahead and post it in one of the two rooms. And I'll ask a question in the meantime. So out of curiosity, is there a way to validate that it's not a demand channel? You seem to be postulating that it's a supply channel coming from the bank, but what if it's coming from, I mean, I guess I don't understand how national the loan market is, but what if it's either coming just from increased demand for loans because the firms think they're more exposed, and that raises the price of loans, or if it's coming from firms' demand then telling the banks that there's more exposure and the banks then become more worried about it. Is there any way to do anything on the demand side to kind of control that away or find?
Yeah, that's actually a very important question. So you can see in our design of the setting, we try to reduce the disturbance from the demand side as much as possible. So we actually exclude all the firms who directly affected by the disaster. So for example, like if Katrina hit New Orleans firms, we exclude the New Orleans firms in New Orleans in our test. So basically, we're looking at firms in Houston because the firms in Houston, they're not directly hit by Katrina per se, but based on historical record, they have the hurricane risk. So in this way, we try to minimize this demand side change. Because if you say a firm suddenly have higher demand after disaster, most likely it's because itself is affected by this disaster. So basically, for those directly affected firms, we exclude them. And
I guess my question is a little different. Like I get that you're trying to isolate an indirect effect from firms that are not directly hit, but I guess I'm also wondering if you think that the banks are indirectly affected because they update their beliefs about some other firms, then you might think those other firms update beliefs about themselves and then change their loan demand from that. And so I guess I'm wondering about the channel, whether it could be coming from the firms either directly through greater demand increase in the price of loan or indirectly because the firm's demand is then a signal to the banks to update their beliefs. But it's not clear why the banks should learn any better than the firms themselves learn, I guess.
I think I think the scenario you described will mostly happen if we're testing the loan application, right? So if we basically in that setting, for whatever reason, firms have more needs to the loans, the application will be increased. However, in this corporate loan market, the data itself is a loan approved by the bank. So from this perspective, it's I'm not saying like it's 100% perfect, but it will be less likely affected simply by firms increasing their demand for credit after disaster happened.
Cool. And while Natalie brings the other presenters back on the stage, I'll ask one more question for Andrew Martinez, which is also something that struck me when you were talking. There was a claim about winter storms not being related to climate change, and that wasn't obvious to me because I thought the polar vortices were actually directly associated with climate change. So Andrew was curious about the fact that you don't find effects from the winter weather, if that means there's a misperception of climate change. And there's also a more technical question about the 3-month cutoff that you can read.
Okay, yeah, sure. So thank you. So for the first one, probably I should, because I don't have time to expand more about the disaster type definition in the data. So the winter storm definition based on the data is like normal winter weather events. So like we normally know, doesn't matter there's climate change or not, there are snowing in the winter, right? So it's normally this type of events. It's not like the Texas winter storm I shouldn't say it's storm, Texas snowing storm earlier this March. So this type of events is actually not classified as winter storms in our sample. So I think that's mostly explains we actually don't find a strong results for winter storms based on the disaster data definition because they just identify those regular winter extreme weathers as the winter storm in the data. And the second one, yes, so we actually changed the month cutoff, the disaster month cutoff in our robustness test. So I think up to like 4 or 5 months, the results still holds. And the reason we choose 3 months cutoff is because previous studies in finance, like JV paper by Strahan, they studied the direct natural disaster effect on households. They find that the effect is strongest within the 3 months window. So that's why we choose it as the one we applied in the paper.
Cool, thank you. And I think Mathias and Jeff are both back on stage now. If y'all could turn your cameras on and unmute yourselves. So first, does anybody, I have a question for the group, but does anybody, and we have like 3 minutes left. So does anybody in the group have a question for the others that's burning? If not, I'll pose my question. And it won't be about European and African swallows. Okay, so my question is, I'd like to conclude the session, I'd like each of you to name something that you can take away for your paper from the other 2 papers that you saw. You can take a second to think about it, and whoever's ready first can go first.
I can go first. Well, what I really liked about Jeffrey's paper was this analysis at the individual human level. So in our paper, what we're doing is we're looking at the firm level, but ultimately the firm consists out of different humans working together. So I think one thing, I'm not sure we would do it in this paper, but maybe something that I will try to do in future research is try to connect more extreme weather events or climate change, how it affects humans, how it affects the labor force, and then how it affects firms ultimately. I think that's, I really like Jeffrey's papers, and I also really liked Ahi's paper. I've seen it a few times already. But it's a good paper. Yeah.
Okay, I will go second. Yeah, actually, Mathias' paper and my paper actually already appeared in a few same sessions in different conferences. So basically, I think all the 3 papers are telling the same story, I mean, comprehensively, even though we're taking perspective from different entities. Like Jeffrey's paper is more about individual stuff, and my paper and Mathias' paper about firms, but also about different side of firms. So putting everything together, big picture wise, actually we're talking about the same thing. And I'm thinking like in my paper on the big picture part, because we already cite Mathias' paper, and we should definitely include Jeffrey's paper citation wise into our paper.
Great. And I'm sorry if I mispronounced your names. I realized Mathias pronounced it differently, so I apologize if I got it wrong. And so, Jeff? We can't hear you again. But if Leslie comes back on quickly, we'll go ahead and move on. I'll give him 10 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Oh, that was really good timing.
I think one thing that I took away from both papers, and this is something I've wanted to do for a long time, but these papers really helped illuminate for me some ways to go about it. And this came up in the question as well, is thinking about underreaction. So a lot of my work is on how people react to forecasts and use forecasts to adapt. But in this last paper, we saw, this result about the polar vortex, for instance. Mathias had this very interesting result about underreaction in terms of implied volatility versus realized volatility. This is a huge question for me, is like, to what degree are people actually taking advantage of all the information that's in the forecast that we have right now? And to what degree are they not, and how can we help them take advantage of that in the future? So I don't know how we would incorporate that into our current paper, but it's certainly something that I think is crucial if we're thinking about information policies to help people adapt going forward.
Great, thank you all. That was really interesting. I appreciate the deeper thoughts. That was pretty cool. So I guess now we're basically at the end of the session. I'm supposed to give closing remarks. So in closing, forecasts matter and climate change matters. Up next at 12:30 p.m., we have the keynote roundtable, setting the research agenda, upcoming priorities for adaptation researchers. You can see more information on this slide. We have lots of exciting speakers coming up, and thank you for joining us. I think there might be a final slide, maybe not. Okay, well, thank you. Thanks for tuning in. We'll see you all soon.
Thank you.
Thank you.